Hey everyone, welcome to the lecture for 7.1 on sampling distribution for a sample mean. So a sampling distribution is basically a way to describe a statistic through taking all possible values of the statistic from all possible samples of a fixed size from the population. Wow, that's a lot. So here's how I want you to think about it. You have a population and you're gonna, let's say, pick a sample size, maybe 10, maybe 25, whatever. We'll talk about the importance of sample size later, but just in your mind, think of a fixed number for a sample size. Now I want you to imagine every single possible way that you could take a sample of that size from that population, right? So you have now all these different samples. And for each sample, you're going to compute the mean of that sample. So now you have a data set that's just full of means for all of these different samples. And what happens then is that as n gets larger, or some might say as if once n becomes sufficiently large, then the distribution of those means is approximately normal. So this image kind of sums it up really nicely, in my opinion. So we've got this huge population, and we take all these different samples, but they all have the same size. They all have sample size of 10. And for each sample, we're going to list their X bar, their mean, their sample mean. And then once we get a list of all of the sample means, we're going to plot them in a histogram. And the shape of that histogram will be approximately normal. So that's the idea. This is the beauty of the central limit theorem here. So the central limit theorem says, suppose X is a random variable with a distribution that may be known or unknown. It can be any distribution. So I think this is just fascinating. Using a subscript that matches the random variable, suppose that mu of capital X is the mean of X, right? So again, X is not normal, but it's just some population, or sorry, it's a random variable with a distribution that has the mean of the population. We're writing it mu sub capital X, and then it has the standard deviation. The population standard deviation is sigma with a capital X subscript. Then the cool thing that happens is that when n is large enough, or we might say when n is sufficiently large, the sampling distribution, as we just described previously, is approximately normal. And what this is saying here is that, so X is our original. It's just any whatever random variable, and it has mean mu of capital X, and it has standard deviation sigma sub capital X. And what happens is you, like I said, take all these different samples of the same size of X, all of them, and you take the mean of all of those samples. That gives you X bar, which itself is a random variable. Moreover, this random variable has a mean, and it also has a standard deviation. And we actually know how to relate these two. So the mean of X bar is the same as the mean of capital X. And the standard deviation of x bar is almost the same as the standard deviation of x, but we just have to divide by the square root of n, right? And so remember that n is our sample size. And what we have here in this boxed expression is that not only do we have these structures for the mean and standard deviation, x bar is approximately normal, which is great because we know how to work with normal distributions. So let's talk a little bit about your sample size. So this is just like a quick infographic. If you have a strong skew, maybe like a binomial distribution with a really small or a really large p-value, then you want to make sure that your sample size is at least 25, or else you're not really going to get the normalness, if you will, of x bar. All right, so let's go ahead and work on an example here and just see if we can practice putting these things into play. So example 7.1, an unknown distribution has a mean of 90 and a standard deviation of 15. Sample sizes of n equal 25 are drawn randomly from the population. Find the probability that the sample mean is between 85 and 92. And then find the value that is 2 standard deviations above the expected value 90 of the sample mean. So we have kind of like two parallel universes here. We have x, which is I guess I referred to it as the original distribution, right? The unknown distribution. The original population. The canvas upon which we will paint this beautiful normal distribution. And we are given that its mean is equal to 90 and its standard deviation is equal to 15. And so remember, this is population mean and population standard deviation. We saw earlier that population mean and sample mean, they're computed the same way, but they have different notation, which is like more than anything, I guess, perhaps a bit annoying when you're first starting this course. But we did see that standard deviation actually is computed differently depending on whether or not we have a sample or a population. So it's really, really important that we pay attention to the fact that sigma here is a population standard deviation. All right, and that's really all we know about this thing. So then we're going to have all these samples, right? So we have n equals 25, and we just rip out all samples of size 25 from this population. From there, we get a new random variable, which is x bar, right? And so this is the sample. The sample mean random variable. And we can actually go ahead and compute its mean, because its mean is the same as the mean it came from. And we can also compute its standard deviation by taking the population standard deviation of capital X and dividing it by n. So what we get here is that, well, mu of x was 90. And we also have that sigma of x was 15 and n was equal to 25. So what we have is then 15 over 3, which gives us sorry, 15 over 5, which gives us 3. So what we can write is that X bar equals, or sorry, follows a normal distribution with mean 90 and standard deviation 3. So now what we want to do is we want to find the probability that the sample mean is between 85 and 92. So we know how to do this. We have an Excel sheet that'll compute this for us. So I just wanted to be really clear on what our objectives were. So on part A, it's asking to find the probability that the sample mean is between 85 and 92. And let's just kind of get a feel for where that's going to be. We know our standard deviation is 3. So if I go 1, 2, 3, that's going to put me at 99, 96, 93. Right? So that's how standard deviations work. And then this will put me at 81. So 85 is going to be between the first and second standard deviation on the left-hand side. And then 92 is going to be before the first standard deviation on the right-hand side. So what we're asked to find is just this area right here. So this is the probability that 85 is less than X bar less than 92, because remember, this is not the distribution for capital X. We don't even know what the distribution for capital X is. So this normal curve, this is dealing with random variable X bar, and the designation between capital X and capital X with the bar on top is very, very important. And that goes for the subscripts for mu and sigma as well. So this is what part A wants. It wants us to find that area. And then in part B, they're asking find the value that is 2 standard deviations above the expected value 90 of the sample mean. So remember that the number of standard deviations, if I was going to count the number of standard deviations, I'm talking about a z-score, right? Z-scores count numbers of standard deviations away from the mean. After all that griping over being careful with notation. Okay. So if I want to be 2 standard deviations above the expected value of 90, well, I know my standard deviation is 3. So I can just go ahead and do this by hand if I want, right? So this is 1 standard deviation. This is the second standard deviation. So that'll put me at 96, right? So this is mu plus 2 sigma. But I want to use this opportunity to show everyone how we can use Excel to compute this for us. Like certainly B, that's pretty straightforward. But for A, we know that in order to compute the area under a Gaussian curve, we either have to use some sort of technology for which we have Excel to help us out, or we have to resort to tables, which no. So this is the Excel sheet for chapters 7 and 8. In 7.1, we're going to have our normal distribution, and it's going to ask us for all the green boxes essentially. So we can see here at the top, it's going to ask us for the population mean and the population standard deviation and the sample size. We cannot do problems that rely on using the normal distribution unless they give us the population standard deviation. If they do not give us the population standard deviation, then that's kind of a horse of another color. A similar color, but a horse of another color. So that's going to be a T distribution. And we will talk about that in another section. So we need to feed this machine the population mean, which we saw for example 7.1 on the left was 90. We need to give it the population standard deviation, which was 15. And then we need to tell it what sample size we're using. And so that was 25. So once I give it the standard deviation and sample size, it's able to compute for us the sample mean standard deviation, or the standard deviation for X bar. So now that I have this, I can answer question A. I want to know the probability that X bar is between 85 and 92. So I want to come down here to this table. It's so similar to 6.1 and 6.2. If I come down here to this table, it's saying, hey, I'm going to compute a z-score and a probability. All you have to do is give me X bar. So I'm like, okay, well, I want to know when X bar is between 85 and 92. So I just plug those in. And what's a little bit different now in this chapter is that Excel was programmed to compute the area between curves. So in 6.1 and 6.2, I was having everyone work on the air quotes art of subtracting away area. But now that we're, professionals at that, I figure why not just program this in? It's a lot easier. So it's going to go ahead and spit out for us the probability that X bar is between 85 and 92. And so we see here that it's equal to 0.69972. And for the sake of record keeping here, let's say I was taking a test and I wanted to be able to show my work, what I plugged in, I would just take a screenshot or a little snipping tool of my inputs and say, hey, this is how I computed this area, or hey, this is how I computed my sigma X bar, etc. So for part A, our answer was right here, 0.69972. For part B, we were asked to find the value that is 2 standard deviations above the expected value 90 of the sample mean. So we did this by hand. Really, the question is asking, hey, when Z is 2, i.e., when we're 2 standard deviations above the mean, so rephrasing again one more time, hey, when Z is equal to +2, what is your X bar? So I come over to Excel and I think, okay, so I want to have an X bar be the output. So remember, green boxes, that's all your input. That's where you're putting in stuff. And then the white boxes, that's where everything gets crunched out and Excel does the work for you. So we want to find one that's going to accept a z-score. And the only one that does that is right here in the bottom center. So I'm going to put +2. So remember, positive and negative does matter. If you're negative z-score, you're left of the mean. If you're positive z-score, you're right of the mean. So we're going to put in a +2 and we get a 96. I mean, we already knew this, right? Because we had a really nice, easy integer valued standard deviation. So I want to look at 2 things. One, that we were right. Obviously, of course we were. But also here in the graph shown on Excel, these vertical lines in the light green, they're actually marking off standard deviations. So if I wanted at least an idea, when I plug in Z = 2, I'm expecting to be right here. And that's exactly where we are, right? So this was, and at z equals 2, we see that we're 96. So we've got it verified here in the graph on Excel. We knew it already in our hearts because we understand what standard deviation is. And then we also had Excel compute it for us to 2 decimal places. So again, I've taken a snip from my screen. So I'm on a Windows machine. I press Windows, Shift, and S all at the same time. It allows me to trace with my cursor over my screen and select an area that I want to cut out and copy. It automatically copies to my clipboard. I come over to OneNote, I hit Control V, and I have a little snapshot of the work that I did. So this is a great way to save what you did, what you plugged in, if you want to save it for yourself for notes, if you want to submit it as support for your written work on an exam. Definitely recommend getting good at capturing your screenshots and putting them into OneNote. So again, we were just looking at when my z-score is equal to 2, I'm going to have an x value of 96. In this next example, it's very much the same thing. We're given a random variable, which is the length of time in hours it takes in air quotes over 40, or I guess not even air quotes, literal quotes, over 40 group of people to play one soccer match. And they're saying that it's actually normally distributed with mean of 2 hours and a standard deviation of 0.5 hours. So before, in the previous example, we knew really nothing about X, but here we know that X follows a normal distribution with a mean of 2 hours and a standard deviation of 0.5 hours. So just to be crystal clear, mu X equals 2, sigma X equals 0.5. And then what we'll do is we'll take our samples where n equals 50. And from that, that's how we create our random variable x bar. We know that x bar is going to follow a normal distribution with mean mu x bar and standard deviation sigma x over the square root of n. Moreover, we know that mu x bar is equal to mu x, which was given to us as 2. And we know that sigma x bar, right? So this is always your standard deviation for your distribution. So this is sigma x bar equals sigma x over root n, which is going to be 0.5 over the square root of 50. And what they're asking us here is find the probability that the sample mean is between 1.8 and 2.3 hours. So the question we're trying to answer is, find or compute, I guess I would say, the probability that x bar is between 1.8 and 2.3 hours. So our task is this. So we have Excel that's going to help us do this. So we want to plug in our values from our population mean and our population standard deviation. So our population mean was 2, our population standard deviation was 0.5, and n was equal to 50. So that generates our normal distribution for us for our sample mean. Next, I just want to go ahead and plug in my x bar values, 1.8 and 2.3. And I still get the probability that x is less than, the probability that x is greater than, the z-score and all that jazz. But like I said, I really like having this third line here that just is going to spit out the probability that it's in between. And so we can see right here that our probability of being between 1.8 and 2.3 is equal to 0.99765. And that's a huge area, right? But look at these z-scores. So we've got a z-score 1.80, that's a z-score of negative 2.83. So that's like right there, right? Just shy of 3 full standard deviations to the left. And 2.30, I mean, it's not even on the graph. So yeah, so if we didn't get something, you know, that was, say, very close to almost 100%, that would be a tip off for us that we've done something wrong, because we're looking at this whole area right here. And so this is the probability. In this next example, we want the mean number of minutes for app engagement by a tablet user. And we're given that sorry, I read that wrong. The mean number of minutes for app engagement by a tablet user is 8.2 minutes. That tells me right away. So X is going to be, right? So X is your random variable that measures minutes of app engagement. And what we're seeing here in this very first sentence is that mu of X is 8.2. Suppose the standard deviation is 1 minute. So that's going to give me population standard deviation sigma subcapital X 1.0. And what we want to do is take a sample of 60, n equals 60, so that from here now we're generating our random variable X bar. So we know that we're going to have mu X bar is equal to 8.2 also. And we're going to have sigma X bar is going to be equal to 1.0 divided by the square root of 60. And in case you're wondering why I'm writing this down every time, posterity, if I were a student in this class, I would just go straight to Excel. I wouldn't bother writing this down. I would just plug it into Excel, screenshot it, throw it back in my notes. So the first question is, what are the mean and standard deviation for the sample mean number of app engagement by a tablet user? That's very wordy. What they're really just asking is, what is mu of X bar and what is sigma of X bar? Well, we know mu of X bar is 8.2 and sigma of X bar, as we just said, was 1 over the square root of 60. So if you're among those of us who really enjoys doing things by hand, now's a great time for you to bust out your calculator. And you're going to get 0.129 for your decimal approximation. So now that I know what kind of my decimal approximation is, I'm just going to go ahead and write 8.2 0.129. I don't need to, I just am. So the next thing we need to do here is we need to look at what is the standard error of the mean. Well, what does that mean? So this is another classic case where mathematics calls one thing by many different names. So I don't know if you guys remember, but from chapter 6, we had the idea, or possibly chapter 5, we had the idea that the mean was synonymous with expected value. And so we had a lot of questions because, you know, you'd have a homework question that says compute the mean. And then the next one says, what's the expected value? And you're like, wait, huh? They're just asking you the exact same question back to back, but with using different verbiage. So that's exactly what's going on here again. So the standard deviation for X bar, this is the exact same thing as the standard error of the mean. So B, they're just asking you what sigma of X bar is. Well, we already know what it is. It's 1.0 over the square root of 60. Why are you asking me again, book? All right, then C, find the 90th percentile for the sample mean time for app engagement for a tablet user and interpret this value in a complete sentence. So percentiles, I've intentionally kind of skipped over them for the first part of this term because I just wanted to look at them through the lens of a normal distribution. Don't ask me why. I don't have a really good reason. That was just like my plan, which, well, no comment. So let's look at this normal distribution, right? So we know that X bar follows a normal distribution with with mu of X bar being 8.2 and sigma sub X bar, AKA the standard error of the mean, is 0.129. So sometimes you'll see this as SEM. And I hope you guys like acronyms because you have a lot more coming your way soon. So we want to look at okay, I think that is officially my best one that I've ever done. All right, so we're looking at a normal distribution. It doesn't have to be this particular normal distribution. It could, this is general. You know what? In fact, don't even, let's just say mu. Just in general, any normal distribution. The 90th percentile, what they're asking about is, can you find what value has to go here so that 90% of the area is to the left? That is how percentiles work. So percentiles, even though they're called percentiles, you might think, oh, I bet it's like a percent. Nope, you'd be dead wrong. They are actually outcomes of the random variable, right? You're going to get an X value back. So this needs to be 90%. Oh boy. And then this over here needs to be the leftovers, which we know is going to have to be 10%. So to say that, you know, let's consider an SAT score, perhaps if you were to say, oh, I scored in the 90th percentile, that means that you did better than 90% of your peers for that, whatever cohort testing group, whatever dumb rules they make up. If you got a letter in the mail saying that you scored in the 10th percentile and you were like super excited about that, you're like, oh my God, the top 10%, 10th percentile, those two things are totally different. So if you were instead in the 10th percentile, let's look at what that would be, right? So this is the 90th, this number, this X value, or for us, it's an X bar value, right? So I'm just trying to keep it very general for whatever our distribution is, whatever our random variable represents. Is the 90th percentile, right? It is a number. So if I instead have, man, it's going to be a real shame that I can't draw this as good a second time. If instead, let's say you got a letter saying that you were in the 15th percentile, and you're thinking, oh, that's pretty good. I did better than, I'm like in the top 15%. Nope, wrong. What that means is that this is the number or X value or whatever. It is going to be the 15th percentile. So that's going to be here where 15% of your area or 0.15 is here. And then the rest, the other 85%, is going to be over here. So not only did you get smoked by 85% of your peers, you're literally worse than average because the average, the mean, is above you. So in the first case, I wrote it in terms of percentages. Here, I'm writing it in terms of decimal, but it's the same concept. All right, what were we talking about? Find the 90th percentile for the sample mean time. Okay, sure. So what C is asking of us, C is saying, hey, can you find little x bar? So remember, we use lowercase variables to represent specific outcomes, and we use uppercase variables to represent random variables. So we want to find little x bar, st, such that the probability that capital X bar is less than little x bar, right, is equal to 0.90. So I'm writing what we see pictorially here for the 90th percentile. I'm writing it in terms of a probability equation. So capital X bar is just saying, hey, I want all my random variables to be capped at little x bar. So this is going to be, this is little x bar. And so I want to say, okay, all of these values over here, they're going to make up 90%. And only 10% are going to be above this little x bar. And we actually have a way to do this in Excel. And I'll show you that in a second. So let's just write down what D wants from us. Find the probability that the sample mean is between 8 minutes and 8.5. Okay, I'm like almost tired of this question now. We know how to do that. Okay, so let's do it. All right, so now that we know what our, actually let's zoom on a little bit. We know the kind of the context or the environment of this problem. We're going to have to always start with updating our information for our population mean, population standard deviation, and our sample size. So for this problem, we had 8.2, we had 1.0, and we had 60 was our sample size. So that gave us our sample mean and sample standard deviation. Or I guess I would say it, our standard deviation for X bar. So now we have already done part A. First of all, if we hadn't done part A, guess what? They're right here. Ta-da. We can move to part B. Guess what? We already did that because as we just saw, the standard error of the mean is the same thing as sigma X bar. So already produced, done. Now, probably the hardest part about this problem is figuring out how to compute C with Excel. And by hardest part of this problem, I mean takes more than just sticking in numbers without thinking about it. So first of all, I want us to get an idea of what to expect. So if we're looking at the 90th percentile, we know we need to be somewhere over here, right? We need to be pretty far right. And because we want this area here to be 90%. So if I got something, well, first of all, if I got something that's less than 8.2, forget it. I definitely have to be above the mean. So what I'm going to do here is I have to determine, am I going to use this upper table that says probability that X is less than or equal to X? That really needs to say X bar. Or the probability that X is greater than or equal to X. I can actually do this two ways because as we just saw, we know that this area over here, that's 10%. So if I wanted to look to the right, I would use the bottom table. The probability that X is above this number, that has to be 0.1. And I get my Z-score and I see that my X value is 8.36, whatever. If I wanted to look to the left, well, I need 90% of my area to be on the left. So that's going to be 0.90. Guess what? It gives me the same Z-score. It gives me the same X value. So you're welcome to do it however you like to do it. If you like to keep it left, great. If not, you're welcome to choose either. If you want to do both, more power to you. So for this problem, the only thing that remains to do is 8 and 8.5. So the probability that X bar is between 8 and 8.5, we see now is 0.92926. And then we also saw that our X value for the 90th percentile is about right here. So I was a little north, right? So I kind of guessed at 846 and it was 836, but that's not too bad. So I'm just going to save a copy of what I plugged in, what came out, and I'm just going to throw it right into my work. So next we have some homework questions. I think what I'll do for these ones is I'm just going to show them to you in Excel, and I'll just kind of copy and paste the work into our notes if anyone wants to review it later. So the first thing I'm going to do is I like to start with a fresh slate. So I'm going to go ahead and clean all this stuff out. A company produces steel rods. The lengths of the steel rods are normally distributed with a mean of 153.6. Okay, so I'm gonna stop there. I'm going to type in my 153.6 for my population mean. And it tells me that the standard deviation is 0.7. So this is my population standard deviation. For shipment, 10 steel rods are bundled together. And then we're going to round all answers to 4 decimal places if necessary. So actually, I changed this to 2 decimal places in the homework, so I might just stick with that. So the sample size is going to be 10 rods here. I had a change of heart. I had to go get the updated question so that when you see it on the homework, it matches. So here it is, updated, republished, 2 decimal places. Unfortunately, it regenerated the numbers for our mean and sigma x. So we just got to put those back in. So I have 218 for my population mean, and I have a standard deviation of 1 centimeter. My sample size is 45. So remember we talked earlier in the lecture about when your sample size is sufficiently large. So I think in the textbook that I referenced here on notes is they were saying that, 25 is good enough. I think I will probably definitely look at some secondary sources and see what I can add to that. But for this question, 45 is definitely good enough. So they're just asking me, what's the distribution of X, right? So what they're really saying is like, what's the distribution of the original guy? Well, that's easy. The original guy was just 218 and 1. And you're thinking like, well, how do we know the original guy is normally distributed? Well, it's right there. So we already know. So this is going to be 218. And make sure to put to 2 decimal places. If necessary. Boo, whatever. What is the distribution of X bar? So for X bar, that's the one that's going to give us, we still have 218. We know that. But now we have the standard error of the mean, aka sigma sub X bar. That is 0.15. So I'm rounding to 2 decimal places from 0. I'm taking from here, right? I'm looking here and I'm saying, okay, I'm going to round that up to 2 decimal places. I'm going to skip C. I'm going to go straight to D. For a bundle of 45 rods, find the probability that the average length is between 218.1 and 218.2. So I just put 218.1, 218.2. And I get, so now I'm looking here. So I can see that I get 0.16131, which I'll just leave as 0.16. So now I'm actually going to kind of take a little snapshot of my distribution. And you'll see why in a second. In part C, it's saying for a single randomly selected steel rod, find the probability that the length is between 218.1 and 218.2. So in part C, what they're really just asking for, you could look at it 2 ways. You could say, okay, they're really just asking about the original X, which is a normally distributed function. It's a normally distributed random variable. So that is what we did in chapters 5 and 6. So if I was feeling so compelled, I would just open up my 6.1, my 6.2 normal distribution, and I would just put in my mean and my variance, right? So my mean is 218 and 1, right? And then I want to figure out, okay, well, I need to compute my z-score and probability. So my upper bound is 218.2 and my lower bound is 218.1. So I'm going to take this 57,926 and I'm going to subtract the 53,985. And so what I would get, if I were to do that, I'd just do it on my calculator. So, but I can write on my screen. So 53,983, and I get 0.03943. And so this is the probability of 218.1 X. Wow, that is just atrocious, huh? Okay, much better. So got that squared away. And so I might want to go and grab this and go through it here for my work. But I want you to notice something interesting about what our chapter 7 and 8 Excel can do. If you let n equal 1, notice that sigma x, our population standard deviation, is now equal to sigma x, x bar. That's because when we divide by the square root of 1, we're just dividing by 1. Well, guess what? That doesn't do anything to anyone ever. So now x bar and x have the exact same distribution. So I don't need to bother with going to that other page. In fact, look at, let's compare really quickly. So we end up getting the same value, right? Our probability was 0.03943. Well, that's what we got in our chapter 6 Excel. And we made it happen for ourselves in the chapter 7 one by just forcing n to be 1. So that's an option that you guys have. Do whatever you want. I'm okay with it. So these next questions, oh, you have to answer one more question, I believe. For part D, is the assumption of normal necessary? So when your sample is big enough, you don't need to assume that it's normal. That all comes from the central limit theorem. So if we go all the way back up to the tippy top, I think one of the first things I said was that it's really interesting that x can be any distribution. So long as n is sufficiently large, you're going to have that x bar is approximately normal. In our question that we just worked on, we had a sample size of 45, and I guess I'm just telling you to take it on faith that it's big enough to not have to have x be approximately normal. So I think actually the author of this problem defined big enough as 35. So I'll look into that a little bit more and have some more to say on it later on. So I will leave it to you to complete the rest of the homework. Oh, I will say this one more thing. P69, this is just the value, the x value that separates the bottom 69% values from the top 33. It's the 69th percentile. That's all it means. All right, so now that I've clarified that, good luck, and I'll see you soon.